All right, so here in lesson 82, basically we just have a few problems here. I'm not going to necessarily go through every single one of these. All right, there's two I definitely want to hit. I'm going to do this first one and then do one on Newton's law of cooling. And then if we have time after that, we'll address another one. Okay, but so let's look at this first one here. It says, suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? Okay, so using the rule that we looked at, CE to the KT, how would we figure out a model for this and then hence figure out how many were in the original population?
C is.
C we don't know yet, but then we know the T and Y.
Okay,
For 2 of the days.
very good. We know the T and the Y for 2 of the days.
T is time.
So Y is the number of flies, and there were 100 flies on after 2 days. So CE to the 2K,
NBA 2K.
right? And there are 300 flies after the fourth day. So that's going to be E to the 4K.
Mr. Jackson.
What?
I have a theory.
What?
We can do a system of equations.
We have a system of equations. That's right. Okay.
Cash money.
Now, this one will solve maybe a little bit different because we're dealing with exponential functions instead of linear functions. But how would we solve this one?
System of equations.
Divide them.
Divide. Okay. If we divide, put these in a ratio, in a proportion, 300 over 100 is going to equal CE to the 4K over CE to the 2K. By the way, if you put the bigger one on top, or the one that has the higher power on top, then notice we're going to reduce this fraction and we'll end up with a positive value. Okay? It's a little thing, but just one less thing to mess up if we get negative exponents. Okay? So we know 3 equals, I know C wasn't 0, so I can cancel those out.
Is it just e to the second power?
Yeah.
Would be,
Second.
what do we do when we're
E to
dividing?
the 2K.
Minus.
You subtract exponents, so it's e to the 2k power. All right?
ln3 equals 2k.
Good. ln3 equals 2k.
So ln3 over 2 equals k.
Okay.
All right. So now that we know that,
Is that the way that we should solve it? Because it doesn't seem like every problem will be able to use. It doesn't seem like we'll be able to use this way on every problem. So shouldn't.
I mean, you could. I mean, you wouldn't want to do this if you had 2 linear equations or like quadratics or something. But since these are both exponentials, it works out this way. If you wanted, you could solve this, you know, C equals 100 over e to the 2k, and then substitute that in here.
No, I'm not talking about this. I'm talking about the solving it as a system of equations, because I think yesterday we solved problems differently, and in the homework they are not solving them using systems of equations.
Well, it all depends on what you're given. Some of the ones we were doing before, you were told what the starting amount was. Here we're not told what the starting amount was. We don't know how many we had to begin with. So we got to then figure that part out. We have 2 unknowns. We don't know what the rate of growth is here, the K, or the starting amount. We just have 2 different measurements. Okay? All right, so at this point, we can then plug this in. I'm gonna go ahead and use this equation. 100 equals C times E to the 2 times K. K is ln of 3 over 2. Okay, so I have 100 equals C times E to the ln of 3. That's nice. E to the ln of 3 is 3. By the way, here's a good example of why using your calculator isn't always that helpful. This stays really nice and easy if you leave it in terms of the natural log. So C is 33 1/3. Okay? Now, you should think about the situation. We can't have 1/3 of a fruit fly. So we should say there are approximately 33 flies. Originally. Okay? You would went around to the nearest whole fly.
Ooh.
Okay?
Oh no.
Unless maybe there was one in an egg or something that was 1/3 of the way from hatch. Okay? Alright, so this is the idea that we're working with. Okay? Alright, our second example here in 82 is 4 months after it stops advertising, a manufacturing company noticed that its sales have dropped from 100,000 units a month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will they be after another 2 months? Okay, so here we have a situation, we're talking about exponential decline again, so we can use that y equals CE to the KT. Do we know C or K? What do we know?
Say it's like 100,000.
We know T.
Yeah, C is 100,000, okay? And then E to the KT. We're trying to get our model here. Now it says we do know a particular T. It says after 4 months, we're down to 80,000 units. All right?
Would T be 60?
No.
T equal to 4.
T would be the 4 months, and Y is the units per month, so 80,000. So now if we plug that in, like we did on our previous one, we could figure out what the K is. Alright, so I'll plug in 80,000. That's 100,000 E to the 4K. So I divide and I get a 0.8 is E to the 4K. I take the ln of both sides and I get 4K. So then I divide by 4 and K is ln of 0.8 over 4. Which, what does that equal?
Negative
785. Okay. So negative 0.055785. All right. So now that we have our K, we can write our model. Y equals 100,000 E to the negative 0.055785 T. And then how are we going to answer the question we were asked? No?
like 2 plus 1. 3, 7.
No? what month would we be looking at?
After another.
What, Liam? The 6th month. Or I gotta plug in 6 for T. We are already at 4 months, so we want 2 more months. Okay.
2 plus 4 is 6.
We did the calculus, we just mess up on that simple stuff. Alright, so it's 100,000 e to the negative 0.055785 times 6. Alright, and what do we get there? You get there, Lily. It's the exponent is times 6, yeah, because it's times t.
554. 71554.
Yeah.
55645.
Okay. Okay, so we could say doesn't necessarily say to do this, but I mean that's approximately. They're obviously using some rounded numbers here. But approximately 71,500 units. If we wanted to go to like 3 significant figures or something like that. Okay? All right, now let's take a look at Newton's law of cooling. This is kind of a classic application. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Okay, basically, you guys probably know from science and whatnot that things try to reach a state of equilibrium. In other words, if I have something that's really hot in something that's really cold and I let it sit there long enough, it'll all end up being about the same temperature. Okay? That's why ice melts on a hot day, because the coldness of the ice is trying to reach an equilibrium and it's trying to warm up the the outside. Okay, which it doesn't really accomplish, and that's why the ice evaporates completely. Eventually. But this is why, if you put, let's say you're baking something, you're putting something in the oven. You heat the oven up to 375 degrees. If you put something frozen in there, okay, it's going to lower the whole temperature of the oven for a while. Okay? That's why in cooking sometimes they'll say, like with meat or whatnot, they'll say, let it sit out on the counter and kind of, take it out of the fridge, let it sit out on the counter for a while and come close to room temperature before you start cooking it, because then it'll cook faster, okay? And your oven won't have to work as hard either. You'll get a more even cook too. But anyways, this is the whole idea, this desire for equilibrium. The rate of change is proportional to the difference, okay? This is why, believe it or not, if you put cold water on the stove to boil, it'll boil faster than if you put lukewarm water on the stove. Which seems totally counterintuitive, but it actually works, okay? Because the rate of change, it'll actually warm up faster if you started with cold than if you started with lukewarm. Because the difference, the difference in contrast is so much different.
I think when it's really, really cold outside, and you get inside your car, you heat it really fast. And when it's a little cool outside, you get in your car, you probably heat it as quickly.
Yeah, it takes you a little bit longer.
Yeah.
So, all right, but let's look at what we're dealing with. Basically, this is saying that we can use this rule we were just looking at. The y equals CE to the KT. Okay? Y equals CE to the KT. All right, so it says, let y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. if the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? Okay? So let's start thinking about, what we could do to solve this problem here. What do you guys propose first?
Well, we could take a look at what could be E, K, and C and everything.
Okay,
Okay,
what are C, K, and T? Do we know any of those?
Okay, we know something about T. We know that
It's time.
yeah, I get it. In 10 minutes, in 10 minutes it cools down. So we know that at T equals 10, it is like 10% less. The object.
Okay.
Temperature. So if Y is the object's temperature, then Y of 10 equals, I would assume, Y, 10% of Y of 0.
It's equal to 90.
90.
Okay, well, yeah, and it's 90.
No, but I'm talking in terms of percent.
Well, let's not mess with percents. We don't need,
Okay.
we'll be able to figure out the K, that rate, later on if we just come up with some points to begin with. Now, you mentioned Y of 0. What is Y of 0?
100.
100.
Y of 0 is 100, which in our model is C, right? So this one's kind of nice. We were told what the starting amount is. All right, let me get rid of.
How do we know that this is the CE to the KT function? Because it doesn't seem to me like.
Okay, now this is not proportional to the temperature itself. It's proportional to the difference between the object's temperature and the temperature of the surrounding medium.
Yeah.
I forgot that part. Okay.
That is why I was confused.
So, the Y is not just a CE to the KT. Okay? And C is not Y of 10 or Y of 0. C is the starting difference. Okay? What's the starting difference?
40.
40. Because the surrounding is 60. So if Y is my temperature, then I need to do 60 plus that difference in temperature. So what's the starting difference in temperature? It's 40. So it would be Y equals 60 plus 40 e to the kt. So that's going to actually change that k. It's going to be different than if I had just done 100 e to the kt. Okay? So I forgot about that initially, but it's a difference. It's not the temperature itself. So here you have to be a little bit careful. Okay? We have to be a little bit careful. But now the process is the same as all of our other ones. Okay? We're going to plug in the point we know. We know at y equals 10, or I'm sorry, at t equals 10, y equals 90. Alright? So I plug in 90 for y, 60 plus 40 e to the 10k. So I need to subtract. So that's going to be 30 over 40. 3/4 equals e to the 10k. So I have ln of 3/4 equals 10k. And that means I have ln of 3/4 over 10 equal to k. Now, if I get the calculator out at this point, okay, 0.75 ln, divide that by 10, and I get k equal to a negative 0.028768. We'll just go to there, okay? So now I know that my model, my final model for the temperature is y equals 60 plus 40 e to the negative 0.028768 t power. Okay? Now, it all had to do with, they told us that y had to represent the temperature, not the difference in temperature. Okay? If I made y equal the difference in temperature, I could just make it y equals 40 e to the kt. Alright? But that's not what we were asked to do. Okay? Now, we did want to find out how much more time is it going to take for the temperature to decrease to 80 degrees. It's already taken 10 minutes. So how much more time is it going to take to decrease to 80 degrees? Well, that's just a simple matter of plugging in 80 for y. 80 equals 60 plus 40e to the negative 0.02768. 0.02878 t power. I subtract 60, I divide by 40, I get a half. Take the ln and divide, and t is going to be the ln of a half divided by the negative 0.02878. And what do we get for the t?
24.
24.094. Now it asks for how much longer. So we are already at 10 minutes, right? So our final answer should be 14. Okay? So therefore, 14.094 minutes longer. Okay? Any questions?